problem at all. Right? You can switch the integrating order of x, y with no problem at all as long as you keep these numbers correspondingly. And that's about it. Okay? And then we move to y simple region. The y simple region where r is bounded between two numbers of x and two functions of y. In this case, I can only write down this double integral in one of the integrating order, where x is between a and b, y is between g1x, g2x, f x, y, dy, dx. So if it is y simple region, y goes interior and x is in the outside. Right, this is the only chance I can go. And also, if it is x simple region, I have r is bounded between two numbers of y and two functions of x. So if it is x simple region, then I need to integrate the x first. So it's going to be from c to d, from h1 of y, h2 of y, f x y, dx dy. So if it is x simple, I integrate x first. If it is y simple, I integrate y first. And then we also practiced how to change these two types back and forth. All right? So we have one region, it can be identified as both y simple and x simple. But one of the integration is much more simpler. So we have to switch them back and forth. Okay, so we have to identify all the required information here and then transform all the things into the other required information. All right, so this is what we did before. And then we switch into a polar coordinate system. And in polar coordinate system, some questions, especially if you're dealing with the case where the integrating region is a disk or a piece of disk, it's going to be much more, or torus. So it's a polar rectangle where theta is bounded between two angles. R is bounded between two radii. And then integrating from alpha to beta, from A to B, f r cosine theta, r sine theta, r dr d theta. And keep in mind, we have one extra factor r coming here. And in the end, we mentioned about the polar r simple region, where theta is still between two angles, and r is between two functions of the angle. So in this case, I can rewrite this double integral from alpha to beta, from h1 theta to h2 theta, f r cosine theta, r sine theta, r dr d theta. So putting them together, we actually have 5 different types of regions in double integral. Okay, so the rectangular region is the easiest. So very likely you will not see that very frequently. This is just too simple. It has nothing to test on. And then these other 4 types of regions will be frequently seen here. Okay, you should be able to know how to identify one of them, and then how to transform from one type to the other. Okay, so you definitely have to be very, very smooth about all these 4 different types of regions in order to do good in the triple integral part. Okay, so in triple integral, we'll be staring at this formula for the majority of the following several weeks. Oh, we have a spring break coming, right? Next week. So you can practice your triple integral. So triple integrals, naturally, we're going to take integrating function involving 3 independent variables. And integrating function involves x, y, z, 3 independent variables. Integrating region is a solid in our 3. So comparing with what we discussed about a double integral, the main complexification comes from the integrating region again. Okay, so let's go from a 1 dimension where it is an interval, 2 dimension is a region in our 2 three-dimensional is going to be a solid in R3. So you can imagine how many different types of solid you can see in three-dimensional space. Okay, you can have cube, which is the easiest possible case. So cube is the equivalence of interval in R3. A right angle is the equivalence for interval in R2, right? So this thing is interval, right? So the cube in R3 is going to be x is bounded by between A and B, y is bounded between C and D, and z is bounded between P and Q. Okay, so interval, and interval. So if you want to see what the solid is, so this is the one. I've been practicing for a lot, so I'm gonna show you off. This is the one. Okay, so if you put this into x, y, z, so x is between A and B, y is between C and D, z is between P and Q. Okay? So basically, it's a Cartesian product of three intervals. Okay, this is the easiest case, which means we want to begin from this easiest case. So still, I will introduce you, I think 7 to 8 different types of solids. Okay, 7 to different types. But we want to begin from the cube. So I want to refer back to this double integral constantly. I want to refer back to this double integral constantly for two main reasons. One reason is this information is required. Okay, this information is required in our identified region in the R3. Second, I want you to constantly practice your knowledge on these double integrals. Okay, so I want to constantly practice it. So not only want to identify the region, but also if it is possible, I can transform one region from one type to the other, right? So when I do that, usually I want to switch the integrating order, right? Usually I want to switch the integrating order. There are a lot of practical reasons for us to do that. For cube, it is the easiest because you can write down in whatever order you want, okay? Because they're all intervals. So from P to Q, from C to D, from A to B, f, x, y, z, dx, dy, dz. Again, I can write down it in whatever order I want as long as I keep these intervals corresponding. So x, a, b, y, c, d, and z, p, q. I can write this in dx, dz, dy. I can write down it in dy, dx, dz. I can also write down it in dy, dz, dx. In fact, I can write down the integrating order in 6 different types, right? dz, dx, dy, and dz, dy, dx. So if you ever learn about any permutation or combinatorics before, I'm just ordering my x, y, z in 6 different orders, okay? Okay, so keep up with me, come on. Keep up with me. This is the easiest case, you don't have to, okay? This is the easiest case, because you can switch the order with no serious consideration at all, as long as you keep your orders correspondingly. For instance, if it is dx, dz, dy, inside I'm supposed to have AP. In the middle, I have P, Q, and outside I have C to D. So you can switch the order as you please, and as long as you keep the 6 numbers correspondingly for these integrating variables, then you're good. There are a lot of practical reasons for us to do that. Because for a function, finding the antiderivative, we regard one of the variables as the only variable, versus regarding the other variable as the only variable. Finding the antiderivative can be quite different, right? So we had this experience for a lot. So changing the integrating order is quite practical. And this cube will be one of the beginning types I want to do. And then we'll move forward to discuss Z simple region. So Y simple region and X simple region. Okay, so we'll discuss x, y, z simple region naturally, right? If you compare with the double integral, we have x and y simple region. Now we have z, x, and y simple region. And then we will move to this polar coordinate system in the R3. So there are cylindrical coordinate system. And also have a spherical coordinate system. Okay? So spherical coordinate system, I might be able to even give you some identification of a z simple region in a cylindrical coordinate system. But generally there are 1, 2, 3, 4. No, it's 1, 2, 3, 4, 6, 7. 7 different types of solids as the integrating solid. Okay? That's the triple integral. Okay? So here is my big suggestion. So triple integral and double integral are not that challenging, but they are definitely more difficult than taking derivatives. Okay, they're definitely more difficult than taking derivatives. This is the same principle for no matter if you're taking single variable calculus or multivariable calculus, right? So if you still remember what you did for single variable calculus, integrals finding the antiderivatives is indeed more difficult than taking derivatives, right? So it's only natural they have to be more challenging, but still there is ways we can follow. So one of the most principles to go from double integral to triple integral is, first of all, you have to be very, very good on the triple integral, double integral. You have to be able to deal with x simple, y simple, polar, and r simple region with no problem at all. And then we're going to use that to identify the solids. Okay, we're going to use that to identify the solids. So I want you to practice your double integral so many times such that in triple integral you can feel very comfortable. Okay. So I want to begin from the easiest case, so just to calm you guys a bit. Minus 4 to 4, from 1 to 3, from 1 to e, x, y, divided by z, dz, dx, dy.
The number is a number.
Is a number, so yeah, indeed. So as long as I write down my triple integral, this is a cube. Right, the integrating solid is a cubic solid because all the intervals here, right? It's all the intervals here, so this is a triple integral in the easiest form. And then I can start my evaluation directly. Again, the principle is exactly the same. Like I said, triple integral, double integral, integrating is not the difficult part. How to identify the region is the key. So from minus 4 to 4, from 1 to 3, so finding the antiderivative function for this one with respect to this, what do you have?
X, y, cubed,
minus,
No,
no, it's log.
natural log.
It's x, y cubed log of z. So if you really prefer to use your own, so it's Ln of z. And then evaluate from 1 to e, dx, dy. Okay? Again, there are a couple of remarks I want to give you. I want to give you a couple of suggestions as well. Because now you're dealing with 3 independent variables. Every time if you do evaluation, listen to me carefully. Every time if you do evaluation, keep your variables with you. Okay, keep your variables with you. You don't want to just write E1 because a lot of times you got confused. You want to write down as z equals 1 to z equals z. So you remind yourself, okay, I'm actually plugging in numbers for the variable z. Okay? So as long as we're plugging the numbers from 1 to 3, so z is equal to e, I'm getting a natural log of e, which is just 1. Natural log of 1 is equal to 0. So I have x, y cubed, dx, dy. Again, the same principle and the same suggestion I want to make to you. As long as I evaluate the middle, the very interior integral, I'm supposed to eliminate the variable z, all right? I'm supposed to eliminate the variable z, which means in here, there should be no z. Okay, so if you eliminate the interior variable, you should have the function to be completely independent with. If you still see z here, in the end, you're not getting a number. There's no way you can get a number. the only way you can get the number is after you eliminate one integral, you eliminate one variable simultaneously. Okay? So the antiderivative for x y cubed, where x is the variable, is half of x squared y cubed. Evaluating from x equals 1 to x equals 3 dy, and from 1 to 4. Okay? Am I making minus 4? Yeah. So when x is equal to 3, I have 4y cubed. When x is equal to 1, I have half of cubed. So I have 7 divided by 2 x cubed. I'm sorry, y cubed. Am I right?
What do you mean 9?
Shouldn't it be 9 over 2?
Oh, sorry, I have
9 over 2?
9 divided by 2 minus 1 divided by 2. I have 4y cubed.
4y cubed.
Yeah. So 4y cubed. So again, if I eliminate one of the integrals, I have to making sure this is no x here.
No x.
Okay, so there's no x here. So the antiderivative for 4y cubed is going to be y 4. And then evaluate between y is minus 4, y is equal to 4. So in the end, I get 0. Okay? I get a 0 in the end.
All that work to get 0.
I can still go back and use my simple principle to see whether 0 makes sense. This function with this region is not strictly positive, right?
Yeah.
There are some points in this region where this function is positive. There are some points this integrating function is negative.
Right.
So it is indeed making sense in the end to get a 0. Okay? So this principle is only going to be applicable if your function is strictly positive. Then you have to make sure the number is positive. Okay? Okay, so I give you a little challenge here. Not in computation, not in multiple integral here, but I want you to ask yourself, what does this number 0 mean? What does this 0 mean? Okay. So if we have the integral of a double integral, we have an integrating region, and also we have a surface. So the surface upon the region will define a volume. So we know this is the volume for the double integral. For triple integral, your integrating region is already in R3. You have your graph your function in R4, right? You have to